This talk will be given by Dr. Stacey Jeffrey, who's a senior researcher at CWI since January 2017, researching quantum algorithms and quantum cryptography, a topic that is as exciting as it is obscure for a lot of us, and we will hear quite a lot about it in a second. She has quite a lot of futuristic, exciting, and inspiring ideas to share with us, so please put your hands together and welcome Stacey to the stage.
As we've seen in the last two sessions, this is a very exciting time in quantum computing. It really looks like we are at a turning point where we will soon start to see the first applications being actually run on real quantum hardware. So right now in the research community, there's a real flurry of work towards understanding what we can do with these near-term quantum devices. At the same time, there's just as much effort being put into looking at future, more speculative applications that we don't necessarily expect to run on the kinds of hardware that we'll have in the next couple of decades. And that's the subject of my talk this afternoon, is the wide open future of quantum computing, where we don't restrict ourselves to things that should actually work in the near term, but rather we ask, what if we had perfect quantum computers? The image you see behind me is the interference pattern that you get when you do a certain kind of experiment called the double slit experiment that you might have learned about in a high school physics class. This is a famous experiment because this pattern that you get by sending a stream of electrons through two narrow slits was completely unexpected before quantum mechanics was well understood. And if you know anything about quantum mechanics, you probably know that quantum experiments often yield unexpected phenomena, fundamentally new phenomena. And quantum computing is all about trying to harness these new phenomena to do information processing tasks. So quantum is different, and this allows us to do new and different things with quantum computers. The big question that researchers like myself are asking is, what are these new and different things that we'll do with quantum computers? And the short answer is, we don't actually know exactly what we'll do with quantum computers. So far, we know of a bunch of computational tasks that we can significantly speed up using quantum computers. We've already seen some nice examples today. But for many of these tasks, it's not clear exactly how or if we can actually harness these new abilities into real useful applications. And to give an example of what I mean, one of the first quantum algorithms ever invented was for the problem of database search. So imagine you have a very big database and you want to find an entry with a particular property. For example, you might ask, is there any customer in our customer database whose company name is a misspelling of Widgets Incorporated? Searching for such an entry could take a long time because it requires checking every entry one by one. If you have a database that's so large that it would take a full 8-hour workday to find an entry with a particular property, a quantum computer could do this database search in just a few minutes. However, there's a catch, which is that in order for your quantum computer to search this database, it needs to be stored in some kind of memory that the quantum computer can interact with. So it can't just be in your normal server as it is now. It'll actually have to be stored differently. And this kind of quantum accessible memory will require to do this. It might be very difficult to produce, and it could be very expensive, not only to buy it, but also to keep it running all the time. So it remains to be seen in which context it will actually be worth it to take your whole server and put it in this quantum accessible memory in order to be able to do these faster database queries. But this is definitely a very cool ability to have, and we're confident that in some contexts this will be very useful, even if at the moment we don't know exactly which context. And a lot of what I'm going to be talking about today is somewhat speculative. There's many things we know how to do that seem cool, but we're not exactly sure how they're going to look when we apply them in practice. But that shouldn't make this any less exciting. This is a brave new world in computing, and there's lots of potential for really game-changing applications. One real area of potential for quantum computers is machine learning and optimization problems. We know of a number of applications in this area where we have quantum techniques that we're not completely sure how applicable they will actually be in practice, which is something that should maybe temper our expectations. On the other hand, these kinds of problems are so important and widely occurring that even if our new techniques are only applicable in a certain narrow scope, this could still be a really huge deal. So many of the problems that we want to solve in practice are optimization problems, where we're looking for the biggest, best, cheapest thing in a given set of things. And the set of things might be described by certain properties that we want. For example, you might ask your GPS to find you the shortest route from your home to your office that passes by your favorite coffee shop and doesn't involve any illegal driving. Another example that some of you might be familiar with is portfolio optimization, where you want to find the best distribution of assets in order to achieve some financial objective. Some of these optimization problems are very hard, and one pretty famous example is called the traveling salesman problem. In this problem, you have a map with some cities and roads between them, and you want to find the shortest path that visits every city at least once. Now, this problem is easy to describe, but to actually solve this problem is so hard that we think it's not possible for a regular computer to solve this problem efficiently. And what I mean by that is if you start adding cities to this map, you'll quickly get to the point where your computer requires millions of years or even longer to solve this problem. One of the reasons that I mentioned this problem is that it's a common misconception that quantum computers will be able to solve this problem efficiently, but we actually don't believe that's the case. So some problems are so hard that we think even with quantum computers we won't be able to solve them efficiently. However, in certain special cases of this problem, we will be able to solve them faster with a quantum computer than we could with a regular computer. It will still take a really long time, but maybe you'll be able to add more cities to your map before you get to the point where it's just taking way too long. Now I want to switch gears and talk about a different kind of application of quantum computers. So I've been talking about speedups so far, but there's also certain things we can do with quantum computers that would actually be impossible using regular computers. And to exemplify this, I want to talk about a pretty cool example, which is something called quantum money. So there is something called quantum money, and at this venue, I obviously couldn't pass up the opportunity to tell you about this cool idea. This is based on a fundamental physical principle, which is that if you have files which are containing quantum information, they cannot be copied. This is one of the ways that quantum computers are fundamentally different from classical computers. And so this leads to an intriguing possibility. Suppose you could store some kind of a coin in a quantum memory as a quantum file. This would give you a kind of coin that is impossible to counterfeit. So no one would be able to make copies of this coin. And this idea was first proposed actually back in 1970 by a grad student named Stephen Wiesner. And he was so ahead of his time that it took him more than 10 years to publish this idea. But eventually, it started a whole new field called quantum cryptography. Now, the fact that you can't copy these coins is just the first step. You also need a way for your users to verify when someone gives them a quantum coin, they need to be able to check that it's real. And there are a number of different proposals for how to do this, and they have different properties. So some of them require a central bank to verify all transactions, whereas some protocols allow for anonymous transactions using this quantum money. So there's a lot of active research going on in trying to come up with new and better protocols. But I do want to stress that this is a very, very far future kind of idea. Right now, if you wanted to actually store one of these, if you saw in the first talk of the session, you would need this giant refrigerated cylinder. You're not going to be able to fit this kind of thing in your pocket anytime soon. But this is a very cool theoretical idea, and there are other potential applications to the idea that quantum files can't be copied. So while there's a lot of unknowns in the future of quantum computing, there's also a lot of reason to be excited about these potential applications. Like I mentioned, optimization problems and machine learning. Also these security applications like money and software protection. But Personally, when I look at the future of quantum computing, the most exciting thing I see is the potential for as yet undiscovered applications. As a quantum algorithms researcher, it's ultimately my job to look at all these cool things we know how to do so far and ask, what else can we do? Thank you very much.